motion. And as you see down here at the bottom, it says two-dimensional motion. Everything we've done up until this point has been looked at in one dimension. So we said first, what does one dimension look like? A line, right? Like this meter stick. And we said that when we're in one dimension, how many choices do we have in regards to direction? Two, right? We either go this way or we go this way. Or if it's a vertical line, we go this way or we go this way, right? But that's it. Our choices are limited. That's good for introducing concepts and looking at relationships and establishing guidelines. Okay? It's great for the motion detector if the cart can only move forwards and backwards. And then it just has to worry about, two things as far as direction is concerned, speeding up, slowing down, change direction, all those things, but only in one dimension. But that's not how the real world works, right? We use one dimension to define all of these concepts up here, right? We basically started over here on the left-hand side, and we've worked our way across all the way over here to conservation of momentum. What we're going to do now is we're going back to the beginning, right? Looking at those concepts again, but how do we apply them to two dimensions? The concepts themselves don't change. F equals ma is still going to apply in two dimensions just like it applies in one dimension. But how we mathematically handle that, how we mathematically analyze it, does change a little bit. And that's where the next part of this class comes into, right? Looking at those topics that we've introduced in one dimension, now applying them two-dimensionally. We start off with motion, because that's where we started off to begin with, right? All the way back over here, displacement, velocity, and acceleration. Those concepts are not going to change in two dimensions, but how we handle them mathematically does have to change a little bit. So first, let's start off with projectile motion. Okay. Projectile motion. An object that is thrown or launched into the air whose behavior is subject to the effects of gravity. We call those projectiles. So an object thrown or launched into the air whose behavior is subject to the effects of gravity. Projectiles. Projectile motion is looking at that object moving under the influence of gravity as it moves through two dimensions. So a projectile is an object thrown or launched into the air whose behavior is subject to the effect of gravity. And then projectile motion is analyzing the motion of that object that is under the effect of gravity in two dimensions. Projectiles, objects moving under the influence of gravity, projectile motion, and analyzing the motion of that object as it moves in two dimensions while it's under the influence of gravity. All right. Good there? As far as explaining projectile motion and relating it back to things that we've talked about before, projectile motion, if we neglect air resistance, projectiles are going to follow a parabolic path. And in most cases, because we're dealing with fairly solid objects that are small air resistance, we can assume that to be the case, unless I specifically tell you otherwise. I generally won't. I probably won't, but just keep in mind that in the real world, this necessarily isn't the case. Okay. Remember, we introduce concepts under ideal conditions, right? Like first introducing things in one dimension, and then moving to 2. Even when we move in true dimensions, we have to put some conditions on it to look at the initial ideas, concepts, then we can apply them to new situations. If we can get rid of air resistance, like it says, that projectile is going to follow a nice parabolic path. But if you've watched the motion of an object that is moving through the air under the influence of gravity, but in 2 dimensions, it doesn't always follow that nice parabolic path. The next slide is just restating this, but kind of fun because it has a picture of a frog on it. So, right? Without air resistance, that frog would follow this nice parabolic path. But in real life, it doesn't reach that nice parabola. A really good example of this is sometimes if you've ever watched golf on TV, and you don't have to admit to watching golf on TV if you don't want to, but if you watch the flight of the ball, especially like a drive, sometimes they have a little line that like tracks the flight of the ball so you can see it. You'll see that it starts off going up nice and easy, but then sometimes it almost like drops straight down because of the spin that's on the ball, or if the wind is hitting it, right? So without air resistance, we have that nice parabolic path, but with air resistance, we'll see some deviation from that parabolic path. Depending on how much air resistance there is, that will determine how much of a deviation from that parabola we'll see. Okay? Good there? All right. As far as explaining projectile motion, okay, we're going to start with this picture. This picture is going to be the basis for how we go from, okay, this is what projectile motion is, to now analyzing that motion. Keep in mind, projectile motion is just free fall, but with an initial horizontal velocity. Projectile motion is free fall with an initial horizontal velocity. So first, taking this picture, if we take a look at the red object, what could you tell me about the red object? Just by looking at that picture. It's round, good.
Falling.
It's falling, good.
Could be going up.
Could be going up, that's true. I'll give you that, could be going up, right? How about those things that we use to measure motion? What can you tell me about that red object?
Velocity is increasing.
Okay, its velocity is increasing, or it is speeding up, if, Evan, we assume that it starts up at the top, okay? And we know that because, right, we see that the space in between those consecutive pictures keeps getting bigger and bigger and bigger, indicating that the distance that it travels is increasing, its velocity is increasing, blah, 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 blah. We've analyzed that problem 100 times, right? It's a kinematic equation and stuff like that. But what we're going to do now is, okay, before we just drop that object, but what happens if when it comes under the influence of gravity, it wasn't just dropped, it was thrown or launched somehow in a way that it was already moving once it came under the influence of gravity? What's going to happen? And what we find out is that that horizontal motion that has been added to the objects initially, when it comes under the influence of gravity, does not affect what is happening vertically. The horizontal motion does not affect the vertical motion. That's an important idea. The horizontal motion does not affect the vertical motion. Yes, they are occurring simultaneously, but they are independent of one another. So the horizontal motion does not affect the vertical motion, even though that they are occurring simultaneously, but they occur independent of one another. the standpoint of the red object, right? It got dropped, gravity starts accelerating it at a rate of 9.81 meters per second squared, faster, 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 faster. That's happening to the yellow object as well. But what else is happening to the yellow object? It's also doing what? It's also moving to the right. The fact that the yellow object is moving to the right does not change what gravity is doing to it vertically. Okay? Anybody see the Mythbusters when they shot the bullet? Okay. One person saw the Mythbusters. Okay. So there's an old conceptual problem that goes along with this picture. Okay? It says that what?
They shoot a lot of bullets.
That's true.
That's one way they're trying to make guns.
So they were trying to prove that there's a conceptual problem that goes along with this chapter that says that if you take a bullet and shoot it out of a gun, and at the same time you shoot it out of a gun, notice I can turn my magic pen into a gun just by holding it like this.
Whoa.
Yeah, I know. So
Watch out.
yeah,
You gotta use that in the terrorist thing.
that's
You know, the
poking
fire
the-
gun.
yeah. So, all right, but if you take a bullet and shoot it out of a gun, and you drop a bullet at exactly the same time from the same height, they'll hit the ground at the same time. Okay? Kim, is that a question or you just you knows?
No, I have something to say.
Go
to
ahead.
that question now. My mom did an experiment like this because she's a science and math teacher at middle school.
Okay.
So she actually did something like this with Nerf guns and Nerf bullets.
And
You drop it and shoot it and they hit at the same time.
good, right? And it should. The one thing I would worry about with Nerf bullets is the fact that Nerf bullets are a little more subject to air resistance than, say, like a regular bullet. So that might. I'm glad that it actually worked. So.
Pretty sure we can't use real bullets here.
No. But on Mythbusters they can. So, and what they found out was that they actually they shot the bullet and kind of figured out where it was landing in a really long warehouse, and then they put some cameras there, and they put some cameras at the beginning, and they had a little apparatus set up that would fire the bullet and drop the other bullet at the same time, and they found out that the difference was like 0.00007 seconds or something like that. So it was within the range of their instrumentation and stuff like that. So, but in a much less dramatic example, okay, I have an apparatus similar to that. Okay, and you are correct, Cam. We cannot shoot bullets here. Okay? So I have to use just metal marbles. So here is a spring. I'm going to pull this spring back and sort of lock it in place just like this. Okay? And this marble I just want to see how long it'll go.
From the air conditioner.
Oh yeah, totally. So, are you actually?
Yeah, I can get it the second time.
I mean, but you're,
That's
I was kind of
that's
watching to
tough.
see if you actually were. All right. So, this marble. No, we used the other marble. This marble fits on the end just like this. Okay. For those of you in the back, you might not be able to see, but it's hollow, and the post is going right through the marble. So if I remove the post, it'll just fall straight down. Okay. This one is a solid marble. And I'm just going to put it right here. Okay. I'm going to flip the switch, and when I flip the switch, this post is going to push this marble sideways. It's going to drop out of this one, okay? And we should see that they hit the ground at the same time, okay? Julie, you might have to take a minute from us here. Just to verify. I know. Thank goodness. Yes, we verified that gravity actually works in this room. So,
They did not
Is that-
hit at the same time.
so that would be, they did not hit at the same time. Okay. All right. Are we ready? Here we go. Okay. Okay. You saw the whole thing. Did they hit at the same time?
Yeah,
You can kind of tell from the sound as well. Okay. So we've added some initial horizontal motion to that object. We've added some initial horizontal motion to that object. but that hasn't changed what gravity is doing to it vertically.
Is that the air conditioner doing that?
Not really sure. I've done this demonstration on this table before in this very room, and it's never done this before. So next, I just pulled the spring back a little bit farther, so now the spring's a little bit more crunched up, right? So when it hits the object, it should give it a greater initial horizontal velocity, okay? But because of this, right, regardless of the horizontal motion that we've given this object, it shouldn't affect what happens vertically. So they shouldn't hit the ground at the same time again, all right? Ted, you ready to verify? All right. Sorry, Julie, I should have warned you. I didn't think it was going to shoot that far, so, yeah. But, once again, I know that was actually, you guys nicely protect yourself there. So, so even though we've added that greater initial horizontal velocity, the object still hit the ground at the same time. So, summarizing this before we apply it to a problem situation. Can you hear that? There we go. Start shaking again, now we're really in trouble. All right. The object is going to fall with an acceleration of 9.81 meters per second towards the Earth vertically. That's not going to change, regardless of whether we give it an initial velocity horizontally or not. If we had just dropped both of these objects straight down, right, we know this is true. Gravity affects all objects the same rate, as long as air resistance can be neglected, blah, blah, blah. If that was the case, if we just dropped red and blue, or red and yellow straight down next to each other, what would we see about their two pictures? Where would they end up? If we took a picture of the two of them, where would they be the entire time? Right next to each other, right? Because gravity affects their motion the same, regardless of the fact that one's red or one's yellow or one's hollow, one's not, as long as we can neglect air resistance. Okay? And if we take a look at these pictures here, even though the yellow one now has that horizontal velocity added to it, if you look, right, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, when we reach the fifth picture, where are they? They're at the same spot, right? And then 2 pictures later, where are they? Same spot. 2 pictures later, same spot. 2 pictures later, same spot. So even though we've added that horizontal velocity, the vertical part doesn't change. Horizontally, though, oh, sorry. We can analyze the motion of that object in the vertical dimension using kinematic equations. It doesn't change the fact that, you know, when we drop this object, its initial velocity is 0, and its acceleration is 9.81, and its displacement is however far above the ground it is, blah, 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 blah. We can still analyze the vertical part of that motion using a kinematic equation. Horizontally, as long as we can neglect air resistance, what is that object going to continue to do horizontally?
What?
If we can neglect air resistance, as soon as I shot that marble out, from the horizontal perspective, was there anything to change its motion? There wasn't. If we can neglect air resistance, the acceleration in the horizontal direction is equal to 0.
So there's no air resistance in that? Would it just be like a straight line?
No, because the horizontal part isn't changing, but the vertical part is. So that's where we get the parabolic shape from, because one variable is changing differently than the other variable is. That's why we get the parabolic shape out of it. Its velocity in the horizontal dimension is constant. If acceleration is 0, what does that mean about the velocity? It's constant, right? We said acceleration is a change in velocity. An example of this. Ready? Here we go. consequence of gravity. Okay? Gravity causes it to slow down, stop, and speed back up in the vertical dimension, right? That's just me doing this, okay? But because I was walking forward, it was also moving forward when I threw it. Meaning, what did it continue to do? Horizontally. Move forward. Yes, gravity slowed it down, stopped it, and speeded it up in the vertical direction, but from the horizontal standpoint, it didn't do anything. It didn't change at all. So, if I throw it up while I'm walking and I keep walking, my horizontal motion and the ball's horizontal motion continue to be exactly the same. So where does it land from a horizontal standpoint? Right back in my hand, because it kept going forward, right? You do this in a car, right? If you're driving in a car, I could sit in the passenger seat of the car and do this as the car is moving. And it's going to come back to my hand each time. Because my horizontal motion, the motion of the car, the motion of the ball, all exactly the same. Even though the ball may be slowing down and speeding up vertically, horizontally nothing's changing. Right? What would make it change? How would it not land back in my hand? Okay? If I try and do that out the window, right, that would change it because there's some air resistance there, okay? Evan, the other way that we could do it? Speed up. If I speed up or slow down, because now my horizontal motion would change, but the ball's wouldn't from the time it left my hand to the time it gets back to my hand, right? Or the third thing that I could do, right, well, the fourth thing, I guess, I could speed up, slow down, or change direction, right? If I throw it up in the air and then go around the corner, the ball's not going to turn with me, right? It's just doing whatever it's doing horizontally. Okay? Good there? Questions? Okay. There's our concepts. Let's apply this to a problem-solving situation. So, the sheet that I gave you today is a sheet of problems that introduces us to the idea of projectile motion. And we are going to start on question number 6. Because it's got a funny little play on words and, you know, just a good way to get it started. So. Alright, so question number 6 says, a painter working on a billboard accidentally kicks the bucket of paint.
Wait, aren't they washing windows?
Yeah.
Maybe they're doing like a texture. But you don't know, do you? You don't know, do you?
Yeah, he's painting with a squeegee.
So,
No,
maybe
it's
that's a
one of
roller.
those roller things.
I don't think so.
You can think whatever you want, but see, if I said a guy cleaning windows kicks the bucket, that doesn't what?
Wouldn't they paint the billboard and then put it up?
No,
No.
the billboard's there. They just paint over the old billboard.
Yeah, you just take it down every time and then.
So, yeah, they just paint over the old billboard. So, of course, now they have those ones that have fancy screens that change all the time.
Yeah.
So, you know,
What?
But
Or it's fabric.
What do you mean?
anyway,
Oh, this is the plan.
Evan, can you at least suspend your, your disbelief of this picture matching with this problem so we can do the problem? Okay, thank you. All right, so it says, the bucket leaves the scaffold, which is 15.5 meters above the ground, with a velocity of 10.2 meters per second. When will the bucket hit the ground? How far away from the scaffold is the bucket? So, if we analyze this problem, right, this guy kicks the bucket, okay? Let's say he kicks it behind this guy so it doesn't run into his legs, all right? So he kicks it off of the scaffold this way. But as soon as it leaves the scaffold, what starts happening to it? Gravity starts acting on it, right? Gravity's pulling it in the vertical dimension, right? That's not straight. It's really hard to tell. So gravity starts pulling it in the vertical dimension. So you've got this horizontal motion that doesn't change because there's no air resistance. Gravity pulling it this way. So the end result of that is that nice little parabolic path. Or in this case, half of a parabolic path because it's starting up at the top. Is that good as far as at least conceptually what's going to happen? Yeah. All right, now let's handle this mathematically. In doing these problems, okay, there is a way that I am going to show you how to do these problems. You don't necessarily have to do it this way, but I think if you do it this way, you'll get the right answer more often than not. Okay? So before we start identifying any variables in the problem, we're going to set ourselves up a little worksheet table to help us out. Okay? If there are two dimensions in which this object is moving, we're going to have two sets of variables. One that takes care of the horizontal dimension, and one that takes care of the vertical dimension. Notice I've left a little space in between them, because there's things that we're going to show that are going to be similar between these two dimensions. So we start off, we make ourselves a table. A horizontal column, a vertical column. Now, if we're analyzing motion, we've talked about that there are several things that we want to know about this object in order to analyze its motion. What are some things that we want to know if we're going to analyze the motion of this object? Specifically, its initial velocity, but also its final velocity. Okay. Notice I'm writing these in a column in between the horizontal and the vertical columns that we've labeled there. So we want to know its velocities. How fast was it going at the beginning of this motion? How fast is it going at the end of this motion? What else might we want to know if we're analyzing the motion of this object? Okay, we'd want to know its acceleration because that causes the velocity to change. That's another thing we'd want to know. What else? The time during which this object or this motion occurs. And then, one more thing. Color of the paint. Color of the paints. Displacement is our other thing, right? So, Roxanne, did you say mass?
No.
Who did? Somebody said it over here. So, anyway, because we're dealing, whoever's chicken enough not to say it, for the benefit of everybody, right? We said it was object moving under the influence of gravity. Does mass affect how gravity affects those objects? Right? It doesn't matter what the mass of this bucket is because gravity is going to affect it the same way no matter what. Okay? Now that we've set up our little work table here, now we can start going in and analyzing what it is we're looking for. So, what's the first thing that this problem asks us to solve for? Okay, it says, when will the bucket hit the ground? If it's asking us a when question, it's asking us to solve for what? Time. Okay? So, here's one trick as far as this table is concerned. Is it horizontal time or is it vertical time? And the answer is, it doesn't matter. Because one of the things that we said was, these motions are occurring simultaneously. Yes, they're independent of one another, but they're happening at the same time. So, if we know the time in one dimension, we automatically know it in the other dimension. This row of the table has to be the same both vertically and horizontally. It's the only row that has to be the same vertically and horizontally. All the other ones might be, but that's more of a coincidence than anything. These two times have to be the same horizontal and vertical because they're occurring at the same time. So if we solve for time in one column, we automatically solve for time in the other column. Good there? Okay. All right. The next thing that it wants us to know is what? Okay. How far is a displacement question, right? But how far away from the scaffold? Is it talking about vertical displacement or horizontal displacement? Horizontal, right? Vertical displacement, well, we'll get to that in a second. So, it's asking us for horizontal displacement. Okay. There's our unknowns as they fit into the table. Now, let's start putting our known stuff in. There are two numbers that you can fill in right away on every chart that we do in this unit without even reading the problem. Not initial velocity. The accelerations are two numbers that we can fill in right away without even reading the problem. What did we we say the horizontal acceleration is going to be? 0. As long as we can neglect air resistance, which we will in most problems, horizontally, once this object leaves the scaffold, there's nothing to change its motion. Vertically, though, what's affecting the motion of the object? Gravity. And we know the acceleration of gravity. It's 9.81 meters per second squared. Regardless of the fact that we've now added a horizontal component, that doesn't change what's happening vertically. Vertically, there's still two options. There's still an up option and a down option. What are we probably going to make our acceleration? Usually we're going to make that acceleration down, but if we do, we have to be consistent. Let's start with that because we'll see in a couple of days that's going to be more important that we make it negative. Okay? We can fill those two spots in before we even read the problem. Okay? But now let's read the problem and let's start talking about what do we know. So, what are some other pieces of information that they gave us in this problem? The vertical displacement is going to be what, Roxanne? 15.5, because it says that the scaffold is 15.5 meters above the ground. So that means the vertical displacement is going to be 15.5 meters. Roxanne, which way is it going to fall, or which way is it going to move 15.5 meters? So we're probably going to have to make this negative as well. Okay? What else does it give us in this problem? It gives us an initial velocity, but there's two initial velocities, right? Which initial velocity did they give us? The horizontal. Okay? Because it says, right, it leaves the scaffold. Leaving the scaffold is the same as this ball doing this. Okay? Right when it left the edge of the table, which way was it going? Well, in this case, it was going this way, right? It doesn't start moving downward until after gravity starts acting on it. So at the moment that it leaves the table, it's going horizontally. So if it says it leaves the scaffold with a velocity of 10.2, that means horizontally it was traveling at 10.2 meters per second. What was it doing vertically? Okay? It wasn't doing anything vertically at the moment that it left the table. We refer to this problem as a horizontal launch problem because when it became a projectile, which way is it going? Horizontally. There's one more thing that we can fill in here before we get started on solving for what we need to solve for. Which one, Gabe? Because there's two here, right? Okay. What does the horizontal final velocity have to be? If the acceleration is 0, initial velocity and final velocity have to be what? They have to be the same. So we can plug in 10.2 for the final velocity horizontally. Okay? Question, or are you stretching?
I have a question.
Go ahead.
But it's like, okay, so why is the delta x like not the diagonal of the two?
Because we have to, that would be the displacement of the entire trip. But mathematically, we can analyze each dimension separately. Okay? We'll get to, okay, what is the entire displacement? Okay?
So
but
when it says how far away from the scaffold is the bucket, that wouldn't be the...
I suppose we probably could change that wording to say how far away horizontally is it. I suppose we could say that. So I'll give you that. Okay? We're actually, Evan, that's where we're headed with this is, okay, now how do we put these two things together to analyze the entire trip? But that gets a little bit more complex mathematically. Here, we've basically got one set of problems going on vertically, one set horizontally, that we can analyze separately in a way that we already know how to analyze. We'll get into how do we put them together now to get like a final answer. Okay? So, can we make final velocity vertical 0? Because eventually what happens to the bucket? Hits the ground, right? But just like when we did this problem, right? if I drop the ball, can I make the final velocity 0? Not if I make acceleration 9.81. Because acceleration 9.81 means what's acting on it? Gravity. But if the object stops, is gravity acting on it anymore? Is gravity the only thing acting on it anymore? No. Now the floor has to act on it. So, we've got this set of information, a couple of unknowns. In order to analyze the motion of the object, we go back here, right, to our kinematic equations, the relationships between these different things. How many pieces of information do we need in order to use a kinematic equation? Well, you have 4 variables, right? But we need how many pieces of information? No. 3, right? Do we have 3 pieces of information here? Yeah, we do, on both sides. Does it matter which side we use to get time? No. But, because the bell's about to ring, I'm going to tell you something about this. If you look, if you look at the vertical side, based on the information that was given to you and what you're solving for, you would pick this kinematic equation. If you start plugging things in, using the horizontal numbers, here, 0 for the acceleration multiplied by t, what happens there? That becomes 0, and then you end up with 10.2 equals 10.2. Is that right? Yeah, 10.2 does equal 10.2. But does it get what you want to solve for? No. So just be careful about which equation you choose, right? We'll pick this up on Wednesday.